Welcome to the video lecture on trigonometric substitution. In this video lecture, we're going to talk about integrals involving quadratic expressions and how we can use trigonometric substitutions to help them turn into integrals that we know how to integrate. So when you have quadratic expressions in your integral and no other method of integration works, then making a trigonometric substitution will sometimes turn the integral into a form that we can handle. Below are two examples that have quadratic forms in the integral that we can integrate and one that we cannot currently integrate. So if we start with number 1, we have the integral of x dx over x squared plus 2x. X squared plus 2x plus 3. So where do we even begin when we see something like this? Well, if we look at that denominator, what we'll notice is that its derivative wants to be a 2x plus 2, and we do not have that in the numerator. So this isn't going to immediately be stuff prime over stuff. Something else that we could consider is this denominator factorable? And in fact, it's not. We can't rewrite this as a product of two binomials. But we can factor it a little bit or put it in a slightly different form if we do a process called completing the square. So let's try that on this denominator. X squared plus 2x plus 3. If I take these first two terms, x squared plus 2x, and I try to factor them into a quantity squared, I would have to have inside these parentheses an x and a plus 1. And that would give me an x squared when I FOIL this out. And in the middle, I would get a 2x when I FOIL this out. But what I would also get is a plus 1. And what I need to have is a plus 3. So that means I'm missing 2 more. So x squared plus 2x plus 3 is the same as x plus 1 quantity squared plus 2. So if we rewrite this integral as x dx over x plus 1 quantity squared plus 2, how does that help me? Well, what I can do now is a nice U-Substitution. We have sort of this inner function, x plus 1. So if we let our u be that inner function, then du would be the derivative of x plus 1, which is just a 1 times dx. So du is the same as dx. Now also in this integral we have this lonely x on top, so we're going to need to know what that x turns into. So if we solve this substitution step right here for x, u minus 1 would equal to x. So now we're ready to substitute in all of our pieces. This x on top becomes u minus 1. The dx just becomes our du. And in the denominator, x plus 1 quantity squared becomes u squared plus 2. Now, how does that help me solve this? Well, again, we still don't have stuff prime over stuff, so this is not immediately going to be an ln integral, but this numerator is a difference of two terms, so I can break this up into the integral of just the u over u squared plus 2 du minus the integral of just the 1 over u squared plus 2 du. And doing that helps me because now each of these integrals becomes manageable. The first one is almost of the form stuff prime over stuff. The denominator is u squared plus 2, and the derivative of that wants to be a 2u. Luckily, I have the u on the top, but I'm missing the 2. So if I put it in and counterbalance by a 1/2, then this does become stuff prime over stuff, which has as its antiderivative the ln of the denominator. So this is going to become that 1/2 ln of the absolute value of this denominator. Now the second integral doesn't have that u on top, so we can't make this be an ln. However, we do have a formula for something of this form, and it's not one of our most commonly used antiderivatives, but it is one that does pop up quite often. So this particular one here is of the form 1 over u squared plus a squared du, and that is an inverse tangent. That's 1 over a inverse tangent of u over a plus c. So that's what I'm going to apply to this. Since we have a 2 down here, the a is actually going to need to be the square root of 2. So this is going to be minus 1 over the square root of 2 inverse tangent of u over the square root of 2 plus our c. Now we're not quite done. We just need to finish it off by plugging back in terms of x. So remember that u was equal to x plus 1. So if I substitute that back in, this becomes x plus 1 quantity squared plus 2 minus 1 over square root of 2 inverse tangent of x plus 1 over root 2 plus c. Now you could leave it like that, or you could also recognize that if I did FOIL this back out again, x plus 1 quantity squared plus 2 was exactly this original denominator. So if you want, it's not necessary to do this, but sometimes textbooks will do this. They'll go ahead and square this back out again and rewrite it in terms of that original denominator. So here's my final answer. Okay? All right, let's take a look at this next one. What am I going to do for this next example? I have the integral of dx over the square root of 2x minus x squared. So this does not fit any kind of pattern recognition formula that I have. You might be tempted to think about that because that square root acts as kind of like an outer function, but the inner function g is 2x minus x squared, and the derivative of that wants to be a 2 minus 2x, and I don't have any of that stuff in the numerator, especially that x that I would need. So that's not going to work. So what we're going to try here is something kind of similar to what we did in the last example. We're going to try to rewrite this expression that's under that square root in a slightly different form, preferably a factored type of form. So what we're going to do is complete the square again. Now, I personally find it a little more challenging to complete the square when that leading term, or excuse me, when that highest degree term, this x squared, has a negative in front. So I am going to go ahead and factor out that negative, and I'm going to put it in descending order. So I'm going to put this positive x squared term first, and since the 2x didn't have a negative, when I factor out a negative, I'm going to need to have one in here so that when I redistribute the negative across, I would get back both of these original two terms. Now to complete the square on this, I'm going to think about how I would factor x squared minus 2x. Well, I would need to have an x and a minus 1 quantity squared in order to get x squared in the front, and in the middle term we'd get a minus x and a minus x, which is this minus 2x. But we would also get a plus 1, which I don't have up here, so if we put it in, then these three terms do become this, but I can't just add in a 1, I have to counterbalance with a minus 1. These three terms become this quantity squared. So when I distribute this negative across, I'm only going to change the minus 1 on the end and leave this negative in front of my quantity squared. So this would become a negative quantity x minus 1 squared plus a 1. And just to make it a little bit neater looking, I'm going to go ahead and switch the order around and do 1 minus x minus 1 quantity squared. So this integral turns into now the square root of 1 minus x minus 1 quantity squared. Now by doing that, we've sort of created this inner function which I'm going to let be my u, just like we did in the last example. And the du then is dx, because the derivative of x minus 1 is just a 1. So we're ready to substitute in. The dx on top becomes du, and in the bottom we get square root of 1 minus this whole quantity becomes our u squared. Now this integral right here again is one of these formulas that you kind of need to know, because if you don't, you're kind of stuck, but it's one of these that you don't see all that often, so it's easy to forget. This is the arc sine. Okay, the antiderivative of 1 over square root of 1 minus u squared is the arc sine of u. So this is just one of these formulas you need to know. So this is arc sine of u. So this is arc sine of u plus c. And now if I substitute back in terms of x, then this u becomes x minus 1. And here's my final answer. you look at this last example here, we can't do either of those strategies on this one because there's no middle term. So we can't complete the square on this to try to get it into that slightly factored form and then progress with a U-substitution. So this is missing that middle term which would help us to factor. So that's why currently this one is something that we can't do because there's no middle term. But we're going to learn a strategy on the very next page which will help us deal with this kind of an integral. So if you see something like square root of a squared minus u squared in your integrand, the a here is a constant and the u is our function of x. So it could just be an x squared or it could be some function of x squared. If you see something of this form in your integral, then what we're going to do is we're going to do a trig substitution. We are going to let our u equal a times the sine of theta. And we're also going to have to calculate, therefore, what du is going to be in terms of d theta, and we'll see what that turns into. But most of the time, it transforms our integral into something that we can actually integrate. So let's see why doing this U-substitution is going to work for us. So here's what we're doing. We're letting u be a sine theta. So that means this integral turns into, or this expression here turns into a squared minus, and if I replace this u with a sine theta, and I need to square that because my u is being squared, then this becomes the square root of a squared minus a squared sine squared theta. Both of these terms have an a squared, so I'm going to factor it out. And that leaves me with a 1 from this first term minus sine squared theta. And that is one of our Pythagorean identities. 1 minus sine squared theta is the same as cosine squared theta. And these are now both perfect squares, so I can easily take the square root of them and just get a cosine theta, which is something much easier to integrate than this yucky square root. Okay, so this is called a trig substitution. You want to use this particular expression where we let u be a sine theta whenever you have a constant squared minus your variable squared. We're going to see two other types of trig substitutions in a few moments, but this is the one that you use when the constant squared comes first minus the variable squared. Okay, so use a sine theta when it's of that form. So let's take a look at an example. We've got the integral of the square root of 4 minus x squared all over x squared dx. So this has that form of being a constant squared, the 4, minus our variable squared. So that's what you want to be on the lookout for. So when you see that, then what you're going to do is a U-substitution. Now normally we say let's let u be something in terms of x. This kind of trig substitution is a little different because here we're actually going to let x equal something in terms of theta. I'm going to use theta to represent my angle in my trig function. So we're not actually using u here at all. Now because the constant comes first minus the variable squared, then we want to do a sine, and in order to make the variables, the constants match, I'm going to need a coefficient of 2 in front of that sine so that once I square it, that 2 is going to turn into a 4 so that both of these terms will have a 4 in front. Okay, so this is my a sine theta. I'm letting x equal that a sine theta. Now before I go ahead and plug that in, we also need to figure out what dx is going to be because that's going to change into something in terms of d theta. So to figure out dx, just take a derivative. What's the derivative of 2 sine theta? Well, that would be 2 cosine theta, and then we get that d theta on the side. So wherever I see this dx, I'm going to replace it with all of this. And wherever I see x over here, I'm going to replace it with 2 sine theta. So let's see what it turns into. we get square root of 4 minus 2 sine theta quantity squared over 2 sine theta quantity squared, and this dx becomes 2 cosine theta d theta. So simplifying, you want to simplify and clean up as much as you can first before you start figuring out how to integrate. So under that radical, we're going to get 4 minus 4 sine squared theta. On the bottom, we're going to get a 4 sine squared theta times this 2 cosine theta d theta. The 4, just a little side note over here, remember 4 minus 4 sine squared theta is 4 parentheses 1 minus sine squared theta, which becomes 4 cosine squared theta using that Pythagorean identity. So this whole expression under the radical turns into 4 cosine squared theta. All right, now let's take our square root. Square root of 4 is 2. Square root of cosine squared is just cosine. And now let's start canceling whatever we can here. So I've got a 2 times a 2 on top, which is going to cancel out that 4 on the bottom. And cosine times cosine is cosine squared theta. Okay, so what we have now is cosine squared theta over sine squared theta d theta. So this is what it's now turned into. Now that isn't something that we can just integrate immediately, but we can use some of our identities to help us out here, because cosine squared, remember, is 1 minus sine squared. So I'm going to use that again on top and try to rewrite this integral entirely in terms of sines instead of having both cosines and sines. And I'm going to change the one in the top because if I get a sum or a difference in the numerator, then I can break this up into 2 separate fractions. If I change the one in the bottom, I can't break up a denominator. I can only break up a numerator. So let's change the top to 1 minus sine squared theta over sine squared theta d theta. And now when I do this into 2 separate fractions, 1 over sine squared theta is also known as cosecant squared theta, minus sine squared theta over sine squared theta is just 1. So this has turned into cosecant squared theta minus 1. And that's good news, because what function has cosecant squared theta as its derivative? Well, that's cotangent with a minus sign thrown in. So the derivative of cotangent theta is normally negative cosecant squared theta. So the antiderivative of cosecant squared theta is negative cotangent theta. Minus, what's the integral of 1 d theta? Well, it would just be theta. Remember, the variable that we're integrating with respect to here is theta. So the integral of 1 turns into a theta, since the derivative of theta would be 1. All right, here's our plus c, but we're not quite done yet, because this is our answer in terms of theta, but our original integral was in terms of x. So now what we have to do is go back to our original substitution right here and figure out how to rewrite this answer so that it's in terms of x. And it's not quite as easy as our typical U-substitutions, where we can just replace the theta with our expression in terms of x and be done. This one's not as obvious because of the way that we created our trig substitution here. We don't know what theta is, we know what x is in terms of theta. So to figure this out, what you're going to want to do is take this x equals 2 sine theta and isolate the sine theta. So I'm going to divide both sides by 2. So we know that x divided by 2 is sine theta. Now in this answer down here, let me write it up here a little bit higher so we can see it. What are the 2 things we need to know? We need to know cotangent of theta, and we need to know just theta. Well, the theta I can get right from here, because if I wanted to get theta by itself, I would have to take an inverse sine of that left-hand side. So theta is going to be inverse sine of x over 2. So that's going to go right here. Now I need to figure out cotangent of theta. To get that, we have to draw a little triangle. So we're going to use a little bit of trigonometry here. This relationship right here on a right triangle, and you can draw your right triangle however you want, I'm going to put the angle theta in that bottom right corner. So if I know that sine of theta is x over 2, remember that on a right triangle, sine is opposite over hypotenuse. So the opposite side would be this side, which is my numerator x, and the hypotenuse is over here, and that's supposed to be this 2. So according to this triangle, sine of theta would be x over 2. What would this adjacent side be? Well, you'd have to use Pythagorean Theorem. It's just going to be this hypotenuse squared minus this leg squared, all under a square root. So 4 minus x squared. Notice that that's the same thing that we had initially over here. That should show up again. Now, based on this triangle, what would cotangent of theta be? Well, tangent, remember, is opposite over adjacent. So cotangent is adjacent over opposite, which according to my sides, the adjacent side to the theta would be this square root of 4 minus x squared, and the opposite side would be the x. So that's what we're going to put right here with a big minus in front. So figuring out how to substitute back in terms of x isn't as easy to do as with a normal U-substitution. Typically on these trig substitution problems, you are going to have to draw a right triangle, use your ratio and the corresponding trig function that you started with to figure out 2 of your sides, then use Pythagorean Theorem to find the missing side, and then from that triangle you can find all 6 of your trig functions and use whichever ones you need to convert your final answer back in terms of x. So this is my final solution. Okay? Now the next example that we're going to do is very similar but with a slightly different form. So this time if you see inside of your integral another square root with a u squared minus a squared, notice the difference between this and what we just did. In the last example, it was the constant squared minus the x squared. Here it's the x squared minus the constant squared. So you want the variable to come first, then you want the constant to come second. So if you have that form, the trig substitution that we're going to use that will work for us is to let your variable, your u or your x, be equal to a times secant of theta. So let's see why this helps us. If we see a u squared or an x squared minus a constant squared, then we're going to let our u be a secant theta, and that makes this turn into a secant theta squared minus a squared. So when I square here, I get a squared times secant squared theta minus a squared. Both of these have an a squared, so I'm going to factor it out, and that's going to leave me with secant squared theta minus 1, and that's another one of those Pythagorean identities. So this becomes a squared times tangent squared theta, since secant squared minus 1 equals tan squared. And these are both perfect squares, so this reduces nicely to a tangent theta. So the only difference between these problems and the ones we just did is now you're going to have the variable squared coming first minus the constant squared. That's when you use secant. If you have the constant first, then the variable, then you're going to use a sign. Okay? So on example 5 here, we've got that x squared minus 25. So since the variable comes first, we're going to let that variable x equal a secant theta, and my a here would be that square root of 25, so 5 secant theta. Before I substitute in, let's find out what our dx is going to turn into. So dx will be the derivative of 5 secant theta, so that 5 stays there, And the derivative of secant is secant theta times tangent theta d theta. So this integral becomes on top 5 secant theta tangent theta d theta. On the bottom, we're going to get 5 secant theta quantity cubed times the square root of 5 secant theta quantity squared minus 25. So that's 5 secant theta tan theta d theta over 5 cubed is 125 secant cubed theta. And remember, just a little scratch work here, this square root, when I square that 5, this becomes 25 secant squared theta minus 25. So when I pull out the 25, I'm going to get a secant squared theta minus 1, which turns into a tangent squared. And so the square root of that becomes 5 tangent theta. Now let's start canceling out whatever we can. I'm going to cross off a couple 5s, I'm going to cross off a couple tangents, and I'm going to cross off one of these secants. I'll still have 2 left in the bottom. So what do I have left? I've got this 125, which is in the bottom, and it's a constant. So let's pull that out. I have this d theta on top, and I have that secant squared theta on the bottom. We had 2 of those left. Now think about this. This is 1 over secant squared. Well, what's 1 over secant squared theta the same as? Since secant is the reciprocal of cosine, then 1 over secant is equal to cosine. So 1 over secant squared is the same as cosine squared theta. So let's change it into that cosine squared theta so we don't have to worry about denominators. All right, now how do you integrate cosine squared theta? This is an even power, and we talked about this in a previous video lecture on trigonometric integrals that involve powers of trig functions. When you have an even power on cosines or sines, that's when you want to use those half angle identities. So that's what I'm going to use right here. So the 1 over 125 stays out front, and the half angle identity is a 1/2. I'm going to pull that out front, and then I'm going to have this turn into 1 plus cosine of double this angle. So this is theta right now. When I use this identity, it doubles it and turns it into a 2 theta. So 125 times 2 is 250, and this is going to be a 1 plus cosine 2 theta d theta. If you need to, you can break this up into 2 separate integrals. So we're going to have just the 1 d theta or d theta plus the integral of cosine 2 theta d theta. So what's the integral of just d theta? Well, that's theta. The derivative of theta is 1, so the antiderivative of 1 would be theta. To integrate cosine 2 theta, be careful here, use your pattern recognition. Your outer function is this cosine. Your inner function is this 2 theta, so that's your g. You have to have g prime present in order to integrate this. And the derivative of 2 theta is a 2, which we don't have. So put it in so that you have the right g prime, counterbalanced by a 1/2. And the only part of this that you integrate is that outer function, which is that cosine. The integral of cosine is sine. And it's going to be sine of that same 2 theta, and that counterbalancing 1/2 that we had out front is still there. So when I distribute my 250 across, I'm going to get 1 over 250 times theta plus 1 over 500 sine of 2 theta plus c. Now that's what we want to figure out the answer for, but in terms of our original x's instead of these thetas. So now is where we need to go back up to our original trig substitution step and figure out what this tells us about these pieces here. So step number 1, isolate your trig function here. So I'm going to divide by 5. So x over 5 equals secant theta. Since I have a theta down here, to solve for theta, you just use your inverse trig function. So I'm going to use an inverse secant of x over 5. So this is going to become 1 over 250 times the inverse secant of x over 5. If you prefer, if you don't like inverse secants, you could also change this to 5 over x equals cosine theta, and then you can do an inverse cosine instead. That works too. So you could also write down here 1 over 250 inverse cosine of 5 over x. Okay? All right, now we need to know what sine of 2 theta is, which means I'm going to need to know something about my right triangle. So let's draw our triangle first. I'm going to put my theta down in the corner. And remember that secant is the reciprocal of cosine. So if cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent. So the hypotenuse is the x, and the adjacent side is the 5. Using Pythagorean Theorem, the other leg will be the hypotenuse squared minus the first leg squared. So square root of x squared minus 25. That should look familiar. That's going to be what we started with originally. Now we want to know what sine of 2 theta is. Not sine of theta, but sine of 2 theta. So to figure out sine of 2 theta, you have to use a double angle identity. Sine of 2 theta is 2 sine theta cosine theta. We need to get our angle down to just thetas, not a 2 theta, because this triangle only tells me trig functions using theta, not 2 theta. So once I use this double angle identity, then I can find out sine of theta and cosine of theta by looking at this triangle. So sine of theta is opposite over hypotenuse, and cosine is adjacent over hypotenuse, so 5 over x. So just simplifying that a little bit, this will be 2 times 5, or 10, square root of x squared minus 25 over an x squared. So this becomes 1 over 500 times 10 square root of x squared minus 25 over x squared plus c. And if you want to cancel out here a little bit, you can reduce that 500 slightly and turn it into a 50. And actually, to clean it up even a little bit more, let's take that square root on the top. This is going to turn into a 50, and on the bottom I'll have that 50x squared plus c. And there's my final answer. Okay, so use secant, a secant theta, when it's your variable squared minus your constant squared. Use a sine theta when it's your constant squared minus your variable squared. The last type of trig substitution that we're going to need to use is when you have something of the form u squared plus a squared. So this is the only one that involves a sum. The other two both require having subtraction. So if you have any kind of an integral involving square root of u squared plus a squared, or your variable squared plus a constant squared, then the trig substitution that makes this manageable is to use u equals a tangent theta. So if we let u be a tan theta, then this would turn into a tan theta quantity squared plus a squared, which becomes a squared tan squared theta plus a squared. If we factor out our a squared, we're left with tangent squared theta plus 1, which is an identity, a Pythagorean identity. Tan squared theta plus 1 is secant squared theta. And both of these now are perfect squares, so when I take the square root, this just turns into a secant theta. So using a tan theta works whenever you have a plus sign in between your sum of two squares. Okay, so that's what we have right here. We've got a sum of two squares, x squared plus 9. So that means I'm going to want to let my variable x is expression you write on the left side, and on the right side is going to be that trig function with the correct coefficient. And my a squared is 9, so that means a needs to be 3. So this is going to have to be 3 tangent theta. So what would dx be? Well, the derivative of 3 tan theta is 3 secant squared theta d theta, since the derivative of tangent is secant squared. So this becomes 3 secant squared theta d theta over the square root of 3 tangent theta quantity squared plus 9, which, remember, is going to turn into 9 tan squared theta plus 9, and 9 tangent squared theta plus 9, when you factor out that 9, leaves you with a tangent squared theta plus 1, which changes into a secant squared theta, and the square root of that becomes 3 secant theta. So that's going to become this denominator down here. All of this turns into 3 secant theta. On the top, we had 3 secant squared theta, so the 3's cancel and one of the secants cancels, so we'll just have 1 secant left. Now, can we integrate secant of theta? Yes. Again, this is one of these formulas that if you don't have it memorized, you're going to get stuck as to what to do at this point. You need to know that there is a formula for the antiderivative of secant theta. It's one of these that you need to have memorized. This is just the ln of the absolute value of secant theta plus tangent theta plus our c. So we know how to integrate that, which means we're just about done here. All that's left is to figure out what secant theta and tangent theta are in terms of x's. So that means you go back to your substitution step, solve for tangent theta by dividing by 3. So in fact, this tangent theta is going to be x plus 3. We already know what that one's going to be. But in order to find secant of theta, you're going to need to draw that triangle again. So here's my right triangle. Theta's down here. Remember that tangent is opposite over adjacent. So my opposite side should be the x, my adjacent side should be the 3. And this time when we use Pythagorean Theorem, since these are both the legs, your hypotenuse will be the leg squared plus the leg squared. So this is just x squared plus 9 under that square root. Should look familiar. Okay, it's just your expression that we started with in the original problem. So if this is my triangle, what is secant of theta going to be? Well, secant is the inverse or reciprocal of cosine, and cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent, which means it's this square root on top over the 3 on the bottom. So that's going to go right here. Now technically you can stop here. This is a correct answer. I do want to show you one thing that sometimes the textbook will do. If you notice that both of these have a 3 in the bottom, so you can think of this as square root of x squared plus 9 plus x all over 3. Using some properties of logs, the log of a quotient is the difference of two logs. You take the ln of the numerator minus the ln of the denominator, which is just the 3. And ln of 3 is a constant, and so is this plus c. So a lot of times what the textbook will do is it will absorb this ln of 3, or this negative ln of 3, into this c and make it a new constant. So make it a new plus c. So sometimes in the back of the book, you'll see the answer written this way, where that 3 is mysteriously gone, but what's really happened is they've absorbed it and created a new constant on the side. Both of these answers are correct, okay? So let's try some miscellaneous problems here. Here we want the integral of x squared dx over the quantity x squared plus 1 squared. So what you want to look for is that x squared plus 1, notice that it's a sum of two squares. So whenever you see that plus sign in between your two squares, that's when you're going to use the tangent for your trig substitution. So you're always going to let the x equal this tangent of theta with the appropriate coefficient. And here my a squared is just a 1, so square root of 1 stays a 1, so my coefficient a is just going to be a 1 in front, which I don't even need to write. So in this problem, x will just be tangent of theta. What will dx be? Well, the derivative of tangent theta is secant squared theta d theta. So let's plug in. On top, we get an x squared, so that's going to be a tangent theta squared, times our dx, which is secant squared theta d theta. On the bottom, we're going to get in parentheses tangent squared theta plus 1 quantity squared. Remember your trig identities. Tangent squared theta turns into a secant squared theta, and that's being squared again. So that denominator becomes a secant to the fourth of theta. And on top, we add tan squared theta and a secant squared theta d theta. Now we want to reduce as much as we can. I'm going to cross off two of these secants, so we'll have tangent squared theta over secant squared theta d theta. All right, so now what do? Well, at this point you have lots of options, okay? There's more than one correct way to do this. If you prefer, you could change all of these tangents and secants into sines and cosines and try to reduce from there. If you prefer, you can use some Pythagorean identities. We've got squares on these tangents and these secants. So what I'm going to do, and we did this earlier on another example, is I'm going to use a Pythagorean identity and change this tangent squared theta in terms of secant squared. And I want to do it to the top one because I can break up a numerator, but I can't break up a denominator. So it's better to leave that denominator as a single term, that's secant squared theta, and just maneuver the top. So tangent squared theta is the same as secant squared theta minus 1. And by doing that, now I can split this up into two separate fractions. Secant squared over secant squared is 1, minus 1 over secant squared. Well, what is 1 over secant squared? 1 over the reciprocal of cosine becomes just the cosine. So 1 over secant squared theta is just cosine squared theta. All right, if I break this up, 1 d theta minus the integral of cosine squared theta d theta. The integral of 1 d theta is just a theta. And then what do when we are trying to integrate cosine squared? We did this earlier today as well. This is an even power of cosine. So the only way to integrate that most efficiently is to use that half angle identity. So I'm going to change this cosine squared into a 1/2 1 plus cosine of 2 theta. You double that angle. And what I need to do at this point is, again, break this up into two separate integrals. I'm going to leave that 1/2 out front. The first integral will just be the 1 d theta, and the second integral will be the cosine 2 theta d theta. So the integral of 1 d theta is theta again, plus, to integrate cosine 2 theta, remember your pattern recognition. Here's your f prime, here's your g. You're missing g prime, which is a 2, so you counterbalance. Now you have all three pieces. The only one you integrate is the f prime on the outside, and the integral of cosine is sine of 2 theta, and that 1/2 that we counterbalance by stays put. Now distributing this negative 1/2 across, I'm going to get theta minus a 1/2 theta minus a 1/4 sine of 2 theta. And notice that these two terms are like terms. This is like a 1 theta minus a 1/2 theta, and 1 minus a 1/2 is just a 1/2. So these combine into a 1/2 theta. All right, No more integrals, so we're ready to put our plus c on, but we need to know what this answer is going to become in terms of x's. So we can't stop here. We got to substitute back in terms of x. So go back up here and solve for your tangent of theta. This one actually already is. And it doesn't look like a fraction, but you can make it into one by putting that x over a 1. So on our triangle, tangent is opposite over adjacent. So you can use x for the opposite side and 1 for the adjacent side. Square these both and add them together and take the square root of that to get your hypotenuse. So in terms of my answer down here, we're going to need to know what just theta is, which we can actually get from right here. How do we solve this equation for theta? By just undoing that tangent, which is what an inverse tangent is. So take the inverse tangent of the left side, and that will give you theta. So this is going to be 1/2 inverse tangent of x. Now I need to know sine of 2 theta. There's that double angle identity again. We can't find sine of 2 theta, but if we change it into 2 sine theta cosine theta, both of these I can find from my triangle. So sine is opposite over hypotenuse, so x over square root of x squared plus 1. Cosine is adjacent over hypotenuse, so 1 over square root of x squared plus 1. Square root times the square root makes the square root go away, so the bottom is just x squared plus 1, and the top just becomes 2x. So that goes right here, multiplied by that minus 1/4 that we had out front. So cleaning it up, we get 1/2 inverse tangent of x. This 2 will cancel with that 4, so I'm going to get an x on top and a 2 times this whole quantity x squared plus 1 on the bottom. And there's my final answer. Okay, these trig substitution problems are not short problems. They take quite a few steps, but the alternative is you wouldn't be able to solve the problem without it. So these are powerful strategies for helping us solve integrals that would otherwise be unsolvable. So it's a good method to know, but be prepared to spend a lot of time doing them, and it does take some practice. It's easy to make little tiny arithmetic mistakes with your constants, so just be really careful and go slowly. All right, let's take a look at this next example. We're looking for one of those 3 patterns, either a squared minus u squared minus a squared, or u squared plus a squared. Well, this one obviously has a minus, and the variable comes second after the minus sign. So when that happens, that's when you use your sine function. So we're going to let x, okay, this is the change here. Now we're letting our variable x in here be defined in terms of a trig function. We know we want it to be sine of theta because the x comes second. What should my coefficient be? Well, this one's a little bit different because we have a 1 over here, so you might think that your a squared is 1, which it is, but we have this 9 in front, and this isn't going to factor correctly and end up sort of simplifying nicely unless we can make these coefficients work out well. Ideally, I would like this 9 to go away and turn into a 1 so that these 2 coefficients would match. So what would my coefficient over here have to be so that once I square it, it's going to cancel out this 9? Well, it would have to be a 1/3, because when I square that, it turns into a 1/9, and when I multiply that by this 9, that's going to turn it into a 1 so that it matches this 1 over here. We'll see that all play out in just a moment. Once I make this decision for what x is, now we find dx. So the derivative of 1/3 sine theta is 1/3 cosine theta d theta. And now we're ready to plug everything in. So the x squared becomes 1/3 sine theta quantity squared. Dx becomes 1/3 cosine theta d theta. And on the bottom, we get 1 minus 9 times 1/3 sine theta squared, all raised to the 3/2. So on the top, 1/3 squared is 1/9 sine squared theta times 1/3 cosine theta d theta. On the bottom, we're going to get 1 minus 1/3 squared becomes 1/9 times this 9 is going to make those cancel out. So I'm just going to have a sine squared theta left over, and all of that still being raised to the 3/2. Now is where you use that Pythagorean identity. 1 minus sine squared theta is cosine squared theta. So what is cosine squared theta raised to the 3/2? This is a power to a power. So you multiply. 2 times 3/2 is just 3. So this is actually going to become cosine cubed theta. That's your denominator after you simplify everything. And on the top, we have that 1/9 times that 1/3, which is a 1/27th. And I still have that sine squared theta and this cosine theta d theta. All right, I can cancel one of these cosines. So we're going to be left with sine squared theta over cosine squared theta d theta. So we've got a fraction here. Sine over cosine would be tangent. So you could think of this as a tangent squared theta and do it that way. Or another option we've done earlier today, you could change this sine squared theta into 1 minus cosine squared theta and then break that fraction up into 2 separate fractions. Both options work. Let's just go ahead with the tangent option since we haven't done it that way yet. Sine over cosine is tangent, so sine squared over cosine squared would be tangent squared theta. Unfortunately, there's no function that's obvious that has as its derivative tangent squared theta. There is a function that has secant squared theta as its derivative. That would just be tangent. So if I could change this into a secant squared theta, that would be good. And I can do that because I have a Pythagorean identity. Tan squared is secant squared theta minus 1. So I'm changing that tangent squared into a secant squared because the antiderivative of secant squared theta exists. It's just tangent theta, since the derivative of tangent is secant squared. And the antiderivative of a 1 is just a theta. So here's my answer. I've gotten rid of all my integrals. If you want to distribute that 27 across, that you certainly can. But now we have to turn everything back in terms of x's. So let's go back up to our top here. This is what we're trying to change. And we're going to change it using this statement right here. So how do we solve this for sine of theta? Well, you can divide by 1/3, which is the same as multiplying by 3. So that's going to make this a 3x on the left side. And you can turn that into a fraction by dividing by 1 if you need to. We do need to know what just theta is. So we can get that from here. To solve this for just a theta, you take an inverse sine of that left side. So theta right here will be inverse sine of 3x. Okay, now we need to know what tangent of theta is. So to get that, I'm going to need my triangle. So what we have here is sine of theta equals 3x over 1. Remember, sine is opposite over hypotenuse. So the opposite side is the 3x. The hypotenuse side is the 1. Pythagorean identity, we take the hypotenuse squared minus the leg squared. So 1 minus 3x squared becomes a 9x squared. Looks familiar, right? So what would be the tangent of theta according to this triangle? Well, it's opposite over adjacent. So 3x over square root of 1 minus 9x squared. So that's going to go right down here. And last thing I'm going to do is just reduce this a little bit. So this is x over 9 square root of 1 minus 9x squared minus 1/27th inverse sine of 3x plus c. All right, the next example here. On this one, we have something that looks a little bit different than what we're used to seeing throughout this section. We don't just have our u squared minus a squared because we've got that little x next to our 4. So this one's going to be a little bit more challenging for us. When you have that middle term in there and it's not in a form that you can easily integrate right away, chances are you're going to have to complete the square to make this work. So that's what we're going to do here. We're going to take this x squared minus 4x and I'm going to try to put it into a more factored form. So completing the square would require that I have an x minus 2 quantity squared, so that when I FOIL this out, I'd get my x squared, I'd get my 4x in the middle, but I would also get a plus 4, which I don't have in this original problem. So I would need to subtract off the 4 to make this whole expression equivalent to this one. Essentially what we did is we added 4 and we subtracted 4. And the plus 4 gets absorbed into the parentheses squared. This minus 4 stays put. So this integral now becomes dx over x minus 2 quantity squared minus 4 raised to the 3/2. Now this isn't quite like our typical x squared minus a squared, but it is a u squared minus a squared, where this u is this function of x. And you can even do an actual U-Substitution to make it look more like that. You can let your u be x minus 2. Therefore, du would be dx. And then that turns this integral into du over u squared minus 4 to the 3/2. And that's exactly one of our patterns that we look for when we're doing a trig substitution. Since the variable is coming first and it's subtraction, this is going to need that secant. So this is going to require that this variable here, which now we're calling u, be a secant theta. And the a would have to be 2 because our a squared is 4. So the trig substitution we want should be u equals 2 secant theta. Now, just a little side note here, I'm not going to do it this way, but as you get more proficient at these problems, you can skip this whole U-substitution step and you can just write this as this whole expression x minus 2 needs to be 2 secant theta. And then your dx and your d theta would proceed from there. So you can skip this whole intermediate variable u and just use x's and thetas. That comes with some practice, okay? So I'm not going to do it that way on this particular problem, but that is an option. So if I stick with my u, then du would be the derivative of 2 secant theta, which is 2 secant theta tangent theta d theta. You really need to know those trig integrals and trig derivatives really well for this lecture. So this turns into du, which on top becomes 2 secant theta tangent theta d theta, over u squared, which is this 2 secant theta that's going to be squared. That turns into 4 secant squared theta minus 4, which is 4 times secant squared theta minus 1, which is 4 tangent squared theta. And all of that's in the parentheses that's being raised to the 3/2. The 2 on the bottom of that fractional power means square root. So the square root of 4 would be 2. The square root of tangent squared would just be tangent. But then we still need to cube that. So what we end up with here is 2 secant theta tangent theta d theta on top over 2 tangent theta cubed, or 8 tangent cubed theta. So simplifying, one of these tangents could cancel out, and the 2 will cancel out and turn this into a 4, which I'm going to go ahead and pull out that 1/4 out front. So we'll still have a secant theta on the top, and we'll have a tangent squared theta on the bottom. All right, so now what we have is secant theta over tangent squared theta. Now, we've seen other examples like this today where we have fractions like this. Unfortunately, this one's a little bit different because that secant on top isn't squared, so we can't really use a Pythagorean identity on that numerator and try to rewrite it so that we could break up our fraction. So since that one is not squared, then my suggested alternative would be to convert everything here in terms of sines and cosines and see if that helps us figure out how to solve this. So let's go ahead and convert everything into sines and cosines. Now, secant of theta is a 1 over cosine theta. Tangent is sine over cosine, but it's in the bottom. So remember, 1 over tangent squared theta is the same as cotangent squared theta. And cotangent is cosine over sine. So this will be cosine squared theta over sine squared theta d theta. So one of these cosines can cancel out. So I'll have 1 left. And I still have a sine squared in the bottom, and I'm going to move it up to the top, and I'm going to put that square on the outside and make it negative because it was in the denominator. And the reason I'm putting it in this form is because this is perfect for pattern recognition. You have your inner function g right here, and this just so happens to be g prime, and this outer power is your f prime. So this is ideal. We have all 3 pieces. We don't even need to counterbalance by anything. We're ready to integrate that outermost power right here. So the integral of a -2 power, you add 1 to that, it becomes a -1 over -1 times that 1/4 that was already there, and sine theta stays in front. Now, rewriting this a little bit, the negative times the 1/4 makes this a -1/4, and sine of theta to the -1 is like 1 over sine theta, which as a trig function is the same as cosecant theta. So I'm going to write it that way, plus c. Okay, so now we have our integral solved for. It's just not in terms of x. So we go back to the top. We have -1/4 cosecant theta plus c was our answer so far. Now, we had 2 different variables here. We had u's and we had x's. So we're going to have to figure out what this is in terms of u and then turn that u back in terms of x. So it's going to be a little bit tricky here. Start with your trig substitution, because that's what we used last. Solving that for secant theta by dividing by 2 tells me that secant theta is u over 2. So on a triangle, secant is hypotenuse over adjacent. So this would be u and this would be 2. So that makes this leg the hypotenuse squared minus the other leg squared. Square root of u squared minus 4. So what would cosecant of theta equal on this triangle? Well, cosecant is hypotenuse, which is u, over opposite, which is this square root. So this is going to turn into -1/4 times u over square root of u squared minus 4 plus c. So we're making progress. Now what we need to do is change these u's in terms of x's, and u is just x minus 2. So I can just replace these 2 u's with an x minus 2. If you want, again, just an option, remember that x minus 2 quantity squared minus 4, this right here, was actually x squared minus 4x if you FOILed it out and canceled out your 4's. So if you want, you could rewrite this as x minus 2 over negative 4 square root of x squared minus 4x plus c. And there's our final answer. All right, the next example here, another one with these square roots and quadratics involved. If you look at that numerator, it looks like a sum of two squares, 4x squared plus a 9. So when you see that plus in front of your or in between your two squares, that's when you know to use a tangent for your trig substitution. So we're going to let our variable x be by itself on the left side, and we're going to want to use a tangent theta. The tricky part on this one is figuring out what your coefficient needs to be so that this will reduce nicely. What you want this end coefficient to be after you've simplified is it needs to have a 9 in it so that it matches this 9 so that I can factor the 9 out from both. So how do I make the 4 go away and turn into a 9? Well, if I want the 4 to go away, I would want to divide by it, and then I would need to multiply by the 9. But I want to do all of that before I square it. So I want the square roots of those 4's and those 9's, which means the coefficient I'm going to need here is a 3 on top and a 2 on the bottom. When you square that, the 2 turns into a 4 and ends up dividing out this 4 that's in front of that x, making it cancel out. And then we multiply this by that 3 squared on top, which makes that turn into our nice 9 that we're trying to match over here. Whoops, this should be a 3. So we'll see how all of that plays out in just a moment, but that's what I'm going to choose here. X equals 3/2 tangent theta, which means dx is 3/2 secant squared theta, d theta. So let's write out what this turns into. We get square root of 4 times 3/2 tangent theta quantity squared, that's all my x right there that I want to square, plus 9, all over 3/2 tangent theta to the 4th times this dx, which is 3/2 secant squared theta d theta. So we get under that square root 4 times 3/2 squared becomes 9/4 tangent squared theta plus 9. The 4's cancel, so this becomes 9 tangent squared theta plus 9. So when I factor out the 9, we get tan squared theta plus 1, which turns into that secant squared theta, and the square root of that becomes 3 secant theta. So that's what this whole numerator is going to turn into. Let me just finish recopying the rest of this problem and then we'll finish simplifying. So this whole numerator right here becomes 3 secant theta. The denominator is 3/2 raised to the 4th. So 3 to the 4th is 81. 2 to the 4th is 16, and this will be a tangent to the 4th theta. And this is all being multiplied by this 3/2 secant squared theta d theta, and that's in the top. So what can we cancel here? Well, we can't cancel any of the trig functions, but we can do a little consolidating of our fractions. We've got a 3 times the 3/2, which is a 9/2, being divided by an 81/16. So that's a 9/2 times the reciprocal 1681. Doing a little reducing, that's going to be 8/9. So let's pull that 8/9 out of the way. On the top, we have a secant times a secant squared, which is a secant cubed. And we still have that tangent to the 4th in the bottom. All right, now what do we have to do? How do we deal with secant cubed theta over tangent to the 4th theta? There's probably many ways to do this. Your choice of what you want to do. My thought is, since this is not an even power on that secant, you can't really use your Pythagorean identities very well. So because it's odd, my option or my suggestion would probably to just go ahead and figure out what all of this is in terms of sines and cosines instead of trying to deal with secants and tangents. So that's what I'm going to do. But there's probably other ways to do this as well. Okay, secant cubed theta is 1 over cosine cubed theta. Remember that 1 over tangent to the fourth theta is the same as cotangent to the fourth theta, which is cosine to the fourth over sine to the fourth. So I'm going to multiply by that on the side here. Whoops, I wrote it upside down. So the cosines are on the top and the sines are on the bottom. So that enables me to cancel out all 3 on the bottom, and that'll leave me with 1 cosine on the top left over. And just like in the last example, I still have a bunch of sines in the bottom, but if I move them up to the top with that negative exponent, then that extra cosine that we had left over acts as my g prime. So this is my g, this is my g prime, and this is my f prime. So this is perfect for pattern recognition. I have all the right pieces, I just need to integrate that -4 power. So if I add 1 to it, it becomes a -3 over a -3 with that 8/9 out front. And the sine theta stays inside. Simplifying, we get 8 over -27, and sine of theta to the -3 is like 1 over sine cubed, which is the same as cosecant cubed theta. So there's my antiderivative in terms of theta. Now we need to figure out what it is in terms of x's. So we go to here. To get the tangent theta by itself, we need to multiply by the reciprocal. So I'm going to multiply by 2/3 times that x. So this becomes 2x over 3. So from that I can create my triangle. This is your opposite side, this is your adjacent side. So 2x over 3, which means the hypotenuse is the sum of the squares of both of these legs. So 4x squared plus 9. It should look familiar. So what would cosecant of theta be? Cosecant is hypotenuse, square root of 4x squared plus 9, over opposite. And we want that cubed. So this is going to turn into -8/27 times the square root of 4x squared plus 9 over 2x, quantity cubed plus c. Cubing this, there's not really a whole lot of simplifying on that top. You can just leave it as square root quantity cubed using parentheses. Another option that's also correct would be to change this to fractional powers. The cube is on top and the square root means this is a fraction of a half. So you could write it that way if you want. And on the bottom, when I cube 2x, that becomes 8x cubed. So these 8's are going to cancel. So we'll have -4x squared plus 9 to the 3/2 all over 27x cubed plus our c. Okay, the last example that we have looks like this, and this one is just a little tiny bit different because now we have some bounds. So I want to show you how to deal with bounds when you have a trig substitution problem. So first let's identify what kind of trig substitution we're going to make. We've got our variable squared minus our constant squared. So the variable coming first with a subtraction means that you want to do a secant for your trig substitution. Now the a squared is 3, which means the a by itself would be the square root of 3. So we're going to need to let our x equal square root of 3 times secant theta. So dx would be square root of 3 secant theta tangent theta d theta. So I'm going to leave off my bounds initially here. We'll deal with those at the end. Let's figure out what the antiderivative is first. So leaving off the bounds for now, this becomes the square root of 3 secant of theta quantity squared minus 3 over square root of 3 secant of theta, that's my x, and then my dx is square root of 3 secant of theta tangent theta d theta. Now a little scratch work for this part right here. That's going to become, when I square this, 3 secant squared theta minus this 3. So when I factor out the 3, we are left with secant squared theta minus 1, which becomes a tangent squared theta. And then to reduce that, the square root of 3 stays put. We can't really reduce that, but the square root of tangent squared just becomes tangent. So all of this becomes root 3 tangent theta. All right, now we start crossing off whatever we can. A couple of these root 3's can cancel. The secant theta can cancel. I still have one root 3 left, so let's pull that out. And I have a tangent times a tangent, so that's a tangent squared theta d theta. Now, as I mentioned before, on these trig substitution problems, because you're using so much trig stuff, you really need to know your trig derivatives and trig integrals really well as recalling some identities, okay? When I see tangent squared theta, I need to know that that does not have an immediate antiderivative. It is not the derivative of some function. But secant squared theta is an antiderivative of tangent, or is a derivative of tangent. So if I change this to secant squared theta minus 1, then that makes this be making progress so that I can get to that final antiderivative faster. So you need to have practice and experience with recognizing that once you get to here, you need to change it to secant squared theta minus 1, because the integral of secant squared theta is just tangent theta, and the integral of 1 is just theta. So this is root 3 tan theta minus root 3 theta. And actually I'm going to take off my plus c because this one did have some bounds. So now we're going to use some bounds here. Now you have two options when you do substitutions. You can either take this answer and substitute back in terms of x by drawing your little triangle here and then use these x bounds. That's perfectly fine. What I find is sometimes easier to do on problems like this is to convert these x bounds into theta bounds so that I can just go right from here and plug in the two theta bounds and get my answer. So that's what I'm going to show you. So to figure out how to do that, you need to go back to here, and we're going to use that for these two x values. So if x was 2, then what would this equation become? Well, the 2 would be on the left side. And if I solve this for secant theta, that becomes 2 over root 3. Now, I personally think of my angles and trig values better in terms of sines and cosines rather than secants. So I'm going to flip this around and change it to cosine theta equals root 3 over 2. So what angle theta, when you take the cosine of it, gives you square root of 3 over 2? Well, the inverse cosine of root 3 over 2 is just pi over 6. So 2 was the upper bound up here, so pi over 6 is the upper theta bound. Now we do this again for the lower bound. So if x is root 3, then what would this equation become? Let's just plug in root 3 for x and see what that tells us theta needs to be. So this becomes root 3 equals root 3 secant theta. When I divide by root 3, I just get 1. Reciprocal of this becomes cosine of theta, and the reciprocal of 1 stays a 1. So for what angle? Remember that when you're doing inverse cosines, you have to think in terms of the domain and range of that. And when you do an inverse cosine, your angle that you get back should just be between 0 and pi. So either the first or the second quadrant. And these are positive values, so we're going to want the angle that lies in the first quadrant. So when does cosine of theta equal to 1? Well, that's just at 0. So my lower bound for x was root 3, so my lower bound for theta is 0. So now that I know my two new bounds, now we can just plug them into here. So if I plug in pi over 6, this becomes root 3 tangent of pi over 6 minus root 3 times pi over 6 minus parentheses, now let's plug in for 0, root 3 tangent of 0 minus root 3 times 0. Tangent of 0 is 0, root 3 times 0 is 0, so all of this just goes to 0. Now you need to know what the tangent of pi over 6 is from your unit circle. Well, that's sine of pi over 6 over cosine of pi over 6. Sine of pi over 6 is a half. Cosine of pi over 6 is root 3 over 2. So this is the same as 1 over root 3. And you can rationalize that if you want, but I'm just going to leave it as 1 over root 3 because that makes it easier to cancel out these root 3's. So this becomes 1 minus root 3 pi over 6. And you can just leave it like that. If you prefer to get a decimal, I believe it's about 0.0931, but you can leave it in this exact form as well. So if you have some bounds, sometimes it makes it a little faster and easier to just convert those x bounds using this trig substitution step right here to figure out what your new theta bounds will be, and then just use those thetas in your antiderivative without having to go through all the work of drawing a triangle and solving in terms of x. Okay? All right, trig substitutions, these are tricky. They take a lot of practice and they take a lot of work. Good luck.